Hi Elijah, how are you? So we got a few people out there. Few problems from test 2 review packet for the final. All right. So which problem in particular do you want to look at? We can do WebAssign questions. We can do any problems you want to do. Do the WebAssign questions first. Okay, well, which WebAssign questions do you have? So the half-life problems on the WebAssign. So let me bring those up. Finding just the time. So let's look at, I'll bring it up so you can see it, problem 8 on the WebAssign question. So the question says that you've got 157 grams this is niobium 259. And it's reduced to 23.5 grams. And half-life here is 58 minutes. The question is, what time was required in order to make this shift to 157 grams to 23.5 grams? Reverse that, sorry. He was more interested in how to find the half-life time. Okay, well, let me find one where it's just the half-life. So question 2, and again I'll put it up on the screen for you to see it. So question 2, what is the half-life, T1/2 of oxygen 22 if 5.11 grams remain from 25.6 grams after 5.23 seconds. So two ways you can approach this problem. One is you can just start with the general half-life formula, and we'll start with that. The amount you finish with equals the amount you start with times 1/2 t to the t over t 1/2. So if we want to isolate the half-life, or we want to isolate the time component, first thing we're going to do is going to divide over the starting mass, or the starting amount. So n over n0 equals 1/2 t over t 1/2. Next thing we're going to do is we're going to take a natural log. You take any log really, but natural log is just the easiest one to work with. So we take the natural log, we get the ln of n over n naught equals, if we take the natural log of a number raised to a number, so if we have the ln of a to the b, it's the same thing as b times the ln of a. So we're going to get t over t 1/2 times the ln of 1/2. And we can rearrange this formula to get ln over n0, ln over 1/2 equals t over t 1/2. So this is another formula. It's kind of rearranged in the notes. I think instead of a 1/2, it's an ln 2, but that's going to flip the n naught over n. That's irregardless. What you end up with is this formula. You know the starting mass, it's ln, or you know the final mass, it's 5.11 over 25.6. The natural log of 1/2 is a number. You know the time is 5.23 seconds. And what you're looking for here is the half-life. So to find the half-life, just bring t 1/2 over to the left side and divide everything on the left side. So we get that the half-life is 5.23 divided by the natural log of 5.11 over 25.6 divided by the ln of 1/2. So really the challenge with this problem is just the algebra associated with it. That's why I give you both forms, the formula and the notes. But yeah, so all you do is just rearrange the half-life formula to solve for the unknown time. And honestly, solving for half-life is the hardest component of this formula, and I'm not going to give you that on the final exam. So typically in class, we're just going to use this as a refresher on how to work with algebra and natural logs. Yeah, the answer number 2 here is 2.3 or 2.2 seconds. All right, Abby, you got any WebAssign questions on test 2? Last problem on the nuclear chemistry. Let me look at what that problem is. So last one is the only actual hard nuclear chemistry problem I can actually give you. It's the only example of this I've ever seen. Oops, not the browser, it would be the desktop I'm looking for. So in this problem, you've got nitrogen 17 plus an alpha particle. And the question is, what does it become? It's an O2 molecule, but what's actually the O2. And the challenge here is that there's actually two of them. And again, this kind of represents the super extreme hard of nucleochemistry problems, which gives you a flavor of how these are not really that hard. So the trick here is that you've got a 2, so this 2 is going to double everything. So really you've got 34 rest mass, 14 charge. Here you still got the 4 and the 2. Whatever oxygen is, you're going to have to double it. So 2 is going to be 16. So you're going to have an 8 there. This will give you 38. So half that's going to be 19, I think. Yeah. So this is how you get to oxygen 19. That doesn't look right. Divided by 2 is 19. What am I missing? Oh, it's oxygen 14. So oxygen 14, 28 will give you 32. And so you divide that 32 by 2, you'll end up getting the 16 back. So it's really just a challenge because you have 2 nuclei, both absorbing the helium atom. And yeah, that's just as hard as it gets. And honestly, that's the only example of that type of problem I've ever seen. Everything else is a single nucleus decay. Half-life problem from the test tube packet. We can, if I were to give you the information, that type of question is not going to be asked on the final. Would that help you out? Would you still want to go over the problem knowing that information? Okay, so we can still do it. So half-life, there's 2 ways to derive half. You can either derive half-life or you can just use the formulas. Which one is it, Abby? Do you want to do it or not? Half-life is something we give you. Half-life is actually important for reactor kinetics. It's more important for chemical engineers than anyone else because you can quickly, if you know the half-life, you can quickly tweeze out like how long it takes a reactor. Working with gases. So that we can definitely do. So in terms of figuring out the pressure dependence of a reaction, let me invent one. So let's say we had this reaction. We had C6H6 plus 2O2 goes to C6H2OH4. And we want to know the pressure dependence of the reaction. And to do this, we're going to have to make a critical assumption that the gas law is elementary as written. Now, as I talked about with kinetics, when we did kinetics in class, that is a huge assumption. Most reactions are never elementary as written. But lack of other information, let's just assume the reaction is elementary. So for any elementary reaction, our rate law is always K, our rate constant, determined by whatever theory we want to apply to the rate constant, times the coefficients, times the concentrations of reactants raised to whatever the reaction coefficients are. So in this case, we've got C6, H6 raised to the first power, and O2 raised to the second power. Now, to figure out the pressure dependence, we're just going to use the relationship that the concentration of species I is just the mole fraction of species I times the total pressure all over RT. And this comes from the ideal gas law. So we can go ahead and just sub it in there. And what we get is that this is K, concentration of C6, H6, times mole fraction of O2, total pressure all over RT raised to the second power. Now, this is easy to do, and it's easy to do because we only have one gas species. If we have multiple gas species, so let's say C6H6 here is in the gas phase, the pressure dependence itself is just P naught over RT raised to the moles of gas. And that will automatically tweeze out your pressure dependence. The challenge with these is recognizing that not all reactants are gases. So this substitution here only applies if it's a gas. Reminds me, this summer I do need to trim the 152 review packets. To make them a bit more focused for what the final is. My exams inherently go deeper because they are focused exams, but your final exam has to be on more topics, so it's a lot broader and less in depth. Pressure dependence? Yeah, it's getting you, yeah. It's kind of interesting how much in this chemistry course, even with all instructors, they teach more of a chemical engineering standpoint on it. It's more meant, this idea of pressure dependence is more focused for reactor design and reaction control. I mean, it's good we teach it, but it's not really fundamental chemistry. Looks like Elijah's about to get 5 new cats. So balancing under basic conditions is actually pretty easy. So I'll do just a simple half reaction. ClO1, there's a ClO2, water. We get 2 H+. So we'll talk about balancing half reactions, and then we'll go over the formulas from test 2. So there is a way to balance a half reaction under basic conditions. I don't remember how to do it because there's a far more efficient method. The far more efficient method is that you balance it under acidic conditions, which you already know how to do for balancing a reaction. And then to convert to basic conditions, what you do is you do 3 things. Step 1, for every H+ you see on the one side, you're going to put an OH- on the right. So in this case, we're going to put 2 OH- on the other side. Step 2, all the H+ get converted to H2O. Last step, any water that appears on both sides, you cancel out. So we've got 1 water molecule here. So we're going to subtract 1 from each side, and this is what we're going to end up with. So those are the 3 steps to convert an acidically balanced redox reaction to a basically balanced redox reaction. Now, the formulas from test 2. If I remember correctly, the only one I gave you, well, actually no, we had a lot. Okay, see what your question is. So yeah, there were a lot of formulas in test 2. And actually, let's take a quick look. I think maybe I give these to you on the final exam. No, I do not. Good for me. So, formulas connecting back to test 2. Luckily, you're not going to have to manipulate too much. These are a lot more straightforward. Again, the exams, because they're subject area exams, can be a lot more in depth. I still don't give you the formulas for a 0 first and second order reaction, and the big reason I don't do this is that these are actually relevant formulas to know down the road. So, formulas for 0 first and second order reaction, these are the concentration versus time. So they're not the rate laws, they're not the R, they're actually concentration versus time. So for a 0 order, concentration of A equals the starting concentration minus KT. So this is going to be your linear one. Your first order, starting concentration, or concentration, starting concentration, E to the minus KT. Your second order, only bother to memorize the useful formula. It can be rearranged to get you the more useful the formula for concentration versus time. So 1 over concentration minus 1 over starting concentration equals KT. So there's your 0 first and second order concentrations versus time. The other formula we used was the formula for method of initial rates. So for method of initial rates, we had that the natural log of rate 1 over rate 2 equals the order times the natural log of concentration of species A over the concentrations, well, so the ratio of concentration A between run 1 and run 2 plus beta, the order on B, natural log of B for the first run over B over the second run. Now, with this, there's also a special case. Well, I shouldn't say a special case. The linear form here, natural log of A equals the natural log of A naught minus KT. So these are really the only 4 formulas you need to know from test 2 material. The relationships between concentration and time, this is just this with a natural log. If you're not comfortable doing that manipulation, then you've got 4 formulas, plus this one from method of initial rates. If you know the rate under the first set of conditions, it's the rate, concentrations under those conditions. R2 is the rate at the second conditions, and the concentrations at the second conditions. Alpha and beta here are your apparent orders. And we have to use the caveat apparent. It looks like it's this order under these conditions. Because we don't have a theory backing us up, we don't know for sure. You're welcome. And you can say this is me, but honestly now, like I've been doing the organic prep, the 0 first and second order comes right back up. SN1 reactions are first order, SN2 reactions are second order. And it has a lot of implications on the speed of the reaction. So balancing the redox reactions on WebAssign, the first problem. So I'll bring it up so you can see it on your screen. So we've got HCrO4 minus 1 goes to Cr plus 3. So balancing a half reaction, we get to manually add the electrons in. If you were doing a full redox reaction, you don't get to do this. You actually have to break the oxidation and reduction reaction into 2 separate reactions, balance those and bring them back together. For this one, first step is always figure out the oxidation. It doesn't matter what you're balancing for redox, figure out the oxidation states. So here chromium is +7. It's going to go to a +3. Because this is a half reaction, we can add the electrons manually. This is reduction. Chromium is getting a more negative or approaching a more negative oxidation state. The other thing, you can do this, I don't advocate for it, but conceptually it makes sense. If it's more positive over here and less positive over here, you're gonna have to add the electrons to the left side. So reduction, the electrons always go on the left side, or if it helps you out, the more positive side needs the more negative electrons. So we've got 4 electrons on the left side. Next step is, once the electrons are balanced, we're going to balance out the oxygens. So we've got 4 on the left, 0 on the right. So we're going to add 4 waters. Last step is to balance the hydrogens. We've got 1 hydrogen here, 8 here. So we need 7 H pluses on the left side, not 4, 7. 7 H pluses on the left side to balance out our hydrogens, and we're done. So that's how you balance a half reaction. And actually, if you go back in the video, you can see that's what's down there. 7H plus 1 HCrO minus plus 3 electrons go to Cr plus 2 plus 4 H2O. Now I'm guessing you'd also like to see a full balancing redox, so let me bring up one of those problems. So we'll do problem 4. NO2 minus 1 plus, oh, I guess I should let you see it. ClO minus 1 goes back and forth to NO plus ClO2 minus 1. So to balance this one, you need to balance your oxidized and reduced species. Here, nitrogen is in a +3, +2 here. Chlorine here is in a +1 going to a +3. So this is our reduced species. This is our oxidized species. So I'm going to split them into 2 separate colors. For our reduction reaction, we have NO2 minus 1 going back and forth to NO. Balance the nitrogens, they're already balanced. The electrons, we go from +3 to +2. So we need to add 1 electron to the left side, and we're not going to balance oxygens or hydrogens in this step. We're going to do that when we bring them back together. For the hypochlorite to chlorite reaction, we have ClO minus 1 going back and forth to ClO2 minus 1. Chlorine is already balanced. This is a +1 to a +3, so this is 2 electrons that have to go on the right side. Now, in order to recombine these reactions, we need the number of electrons gained to equal the number of electrons lost. So we're going to double this reaction. So now it takes 2 electrons. And when we add these back together, they cancel out. So we get 2 NO2 and 2 NO. Now we're back to balancing just the oxygens and the hydrogens. If we look at the oxygens, on the left side we've got 5 oxygens. On the right side 2, we have 4 oxygens, so we need to add a water on the right side. Hydrogen isn't balanced now. Well, we need to go back and balance the hydrogen anyway. No hydrogen on the left, 2 on the right. So we get 2H+. So I've been asked, can we do the second balance on Q in that WebAssign? So are you talking about the Nernst equation? You're welcome. So you mean do the second balance Q in that WebAssign? Oh, so do the second, so you mean problem number 2. Okay, we can do problem number 2. So I'll bring it up for people to see. Second problem, we have, looks like chlorate, ClO3 minus 1, going back and forth to chloride. So to balance this one, chlorine here is in a +5, chloride is in a -1. Difference between this is 6 electrons. And so since we're getting more negative, we're going to add the 6 electrons to the left side. Next we balance oxygen, 3 on the left. So we need 3 on the right. And then we balance hydrogen, 6 here. So 6 here. So the nuclear chemistry section asked what the product of carbon-14 plus an alpha particle is. It was different than what I expected. Is this the homework problem or problem in the packets? So where is this problem? WebAssign. Are you referring to, so I'm looking at the 5 WebAssign problems. There's only one that's an alpha particle capture, and that's the nitrogen. So for that problem, the challenge is there's actually 2 nuclei involved. So because we have 2 nitrogen nuclei, we don't just have 7 protons, we actually have 14. And we don't have a resting mass of 14, we actually have a resting mass of 28. So whatever's on this side is going to have a resting mass of 32 and 16 total. So there's again 2 oxygens, so we're going to have to divide this 16 by 2 to give us 8, and this third 2 by 2 to give us 16. Now the tip off here is that oxygen is atomic number 8, so you knew off the bat this had to be an 8. But this is honestly the only example I've ever seen of an alpha particle capture between 2 nuclei, and quite frankly it's the hardest problem I could ever possibly give you. You're welcome. Section about standard voltage potentials and free energy. So this is something that unfortunately we lose because we're not talking about it in class. And what I do in class is I make you go through and I make you prove the Nernst equation. So there is actually a formula you worked with earlier in the semester, and it was delta G equals delta G naught plus RT ln of Q. And we talked about this with test 3 with free energy change, that the actual free energy change is the reference free energy change plus a correction factor associated with Q, which reflects your real conditions. To convert this to the Nernst equation, you multiply the whole thing by minus 1 over n, the number of electrons, times F, Faraday's constant. And basically this is just a unit conversion. So right now we've got kilojoules per mole. This converts it to volts. The negative here is that we never think about voltage as being negative. We always think about a voltage as being positive for a spontaneous reaction. So we multiply this whole thing by minus 1 over NF, we get delta G over NF equals minus delta G naught over NF minus RT over NF ln of Q. And then we just define these variables as the cell voltage and the reference cell voltage. So we get the relationship that our voltage on our cell is just the negative of the 3 energy change over NF. F here is 96.485 kilojoules per volt equivalent. N is the number of electrons transferred in the reaction, so you'd have to look that up. But I can bring up an example problem. So the first problem that's on WebAssign. Free energy change is minus 148.2 kilojoules per mole. What is the voltage if 2 electrons are transferred? So you're going to take this minus 148.2. Your minus 148.2, it tells you there's 2 electrons transferred, 96.85. and you're going to multiply the whole thing by negative. So minus 148.2 divided by 2 times 96.485 times negative 1 will give you the voltage. Now, voltage range typically 0 to 2, 0 to 3 volts. 3 is kind of pushing it. I think 3.1 is one of those theoretical limits for a single reaction. But that's it. The whole reason for getting you to do this is you realize that voltage is just potential energy. It's the same thing as delta G. It's a chemical free energy, or it's a chemical potential energy that you're using to get useful work out of the cell. But yeah, that's the only connection, is that minus 1 over NF is just a conversion factor. It takes you from kilojoules per mole to volts. And it's volt per electron, but we just kind of leave that off. Yeah, electrochem is really not that, like, until you start getting into like higher courses where they talk about, you know, impedance spectroscopy, electrochem should be very straightforward. It is kind of a witchcrafty kind of field if you really look into like how reference potentials and all that are measured, but yes. So on the final exam on that formula sheet, you're given that formula: I times T times 1.037 times 10 to the negative 5 times nu I over nu electrons times molecular weight equals grams. There's no need to memorize that physical constant. It's actually a ratio of two different constants. If you were an electrochem, I would totally understand you needing to memorize those numbers, but you're not. This is just to give you exposure to it. But on the exam, you are definitely given those formulas. All right, so I've got all his questions answered. I guess the question is if Elijah and Abby have theirs answered. Well, as long as you're over your headache by next week. All right. All right, going back to the voltage and free energy WebAssign. What's your question? A couple more of those. All right. So we'll look at question 3 and question 4. And we'll conceptually talk about how you go through them. So question 3 and question 4 are basically going opposite ways. One gives you the free energy and asks you to find the voltage. One gives you the voltage and asks you to find the free energy. So to do any of these types of problems, what you're going to do is use a relationship that your free energy change, your delta G, is equal, your cell voltage is equal to the negative delta G naught over NF. So N here is your number of electrons, F is Faraday's constant, 96.485. So if you're given the cell voltage and asked to find the delta G naught, which is minus NF times the cell voltage. If you're given the delta G naught and asked to find the cell voltage, you just plug in those numbers. So delta G naught does not have to be negative. In fact, for a non-spontaneous reaction, it's going to be positive. The reason why we have a negative in there is that voltage is considered positive for a spontaneous reaction, and delta G has to be negative for a spontaneous reaction. So the negative is just to create a sign flip convention for voltage. But delta G naught can definitely be positive for non-spontaneous reactions. And the way we view that electrochemically is negative voltage. That's electrolysis. So if you've got a negative voltage, you're not getting voltage from the battery, you're supplying voltage to it to make the reaction go. So an example of this that's done in practice is aluminum oxide conversion to aluminum. So Al2O3 forming aluminum and O2 gas. This is done industrially to make aluminum foil. This is going to have a negative voltage. So the voltage here is less than 0 because we're driving it by electrolysis. And so since the voltage is less than 0, minus NFE is going to give us a delta G that's greater than 0. So the delta G naught, again, doesn't have to be negative. For any battery that produces electricity, produces voltage, the delta G is going to be negative because we're using the spontaneity of the reaction. Any delta G that's negative associated with electrochem reaction, those are considered electrolysis, and the voltage there represents minimum energy to drive the reaction. It's just not likely you've got any batteries sitting around that have a negative voltage on them, unless you hook the terminals up wrong. Yeah, electrochem's easy. I don't understand why so many faculty are kind of intimidated by it. Maybe it helps I did research on it for several years, but even impedance spectroscopy, which requires a little touch of calculus, like if somebody explains to you what it physically means, it's actually not that hard. Converting to basic condition problems. So converting to basic conditions, I'll just put an example reaction up. So do you want an explanation on how it's done, or do you want an explanation about conceptually why we would want to even do it? Both. So practically why we would want to do this. These are reversible reactions. So here the H+ is a product. If we remove the H+ under basic conditions, it makes a forward reaction very favorable. So some reactions, the H+ is on the left side, we'd prefer to keep those acidic, just because the high acidity will drive the forward reaction. But there are reactions like this where they end up producing acid. Basic conditions would make the battery much more favorable to running. So this is in practice why we do this. So if you look at something like an alkaline battery, there's a reason why you would want to run under basic conditions. Now, practically, how do we do it? There's two ways. The correct way is that we would add or subtract the water reaction. So if we go back to test 3, if we have two reversible reactions, we can add and subtract them. So in principle, we could subtract the water reaction twice from this one, and we could generate the basic conditions. The practical way, which is basically if you do this enough times, you'll start picking up on the pattern, is that in 3 steps, we can convert this to basic conditions. Step 1, for every H+ you have on one side, add an OH- to the other side. And the reason being is that if you are doing the water reaction and you're giving me the H+, the H+ are going to be on the opposite side from the H+ you're trying to get rid of. OH- is going to be with it. Second step, all your H+, convert them to H2Os. Third step, final step, cancel out any waters that appear on both sides. So we've got one on this side. So we would subtract it off to give us one on the right side. And that's how you convert from acidic to basic conditions. Now again, you should traditionally be doing this by adding or subtracting the water equilibrium reaction. You can, but this is a nice fast way that will give you the same answer without a lot of the tedious work. And you would use Le Chatelier's to decide if adding acid or adding base would make the reaction more favorable. Yeah, you're welcome. I'd like to think Abby's asleep on her keyboard right now while this plays in the background. So the A refers to the number of, because we generally do this in class. So if we were to add or subtract the water reaction, so we'll go back to our old example, the example we just worked. H2O plus ClO2, back and forth to ClO3 minus 1 plus 2H plus. So there's a K1 here and there's a KW. There's an equilibrium associated with this reaction. If we were to calculate K nu, so the new equilibrium constant, we'd have the old one times the coefficient of water raised to a number. So it's asking you what number would you raise KW to get the new equilibrium constant. Oh, so she logged off. Huh, so it is. Just you and me. So, to figure out K, it's going to be the number of H plus molecules, and whether A is negative or positive. If the acid is on the right side, it's going to be a negative number. If the H plus is on the left side, it's going to be a positive number. So in this case, to figure out the new equilibrium constant, it'd be KW to the -2. And that's all it's asking you for. If you were to calculate a new equilibrium constant based on switching from acidic to basic, what would it be? What's the power on KW? All right, since there's anyone left, got any other questions? All right, so we lost 2 questions. Current mass and WebAssign. All right. So we'll look at the first 2. We won't actually work through them, but we will talk about how to go through them and how to approach these types of problems. So for these types of problems, you're given something and you're asked to figure out how many grams were lost or how many grams were gained on the electrode that's being looked at. So for these types of problems, you've actually got a formula for it, and that you are going to be given this formula in the final, and that is current times time times 1.037 times 10 to the -5 times the coefficient on what you're interested in, coefficient of the electrons, times the molecular weight equals grams. And so if we look at the first one is iron plus 2 plus 2 electrons going to iron solid. And it gives you that you've got 0.2 amps for 120 seconds. So these are very plug and chug kind of problems. Your current is going to go for I. Time, you need to make sure you're in seconds, but that's going to go for your little t. The coefficient is whatever you're interested in. So in this case, it's asking you for solid iron. So we'd use the number in front of the iron, in this case 1. The nu of the electron is whatever the coefficient in front of the electrons is. And your molecular weight, in this case 55.6 grams per mole, is the molecular weight of whatever you're measuring. So that's pretty much how all these problems are solved. You're given a reaction, and you're given a current and a time, or you're given you're being asked to solve for some missing variable in these types of problems. Pretty much you're just going to take this equation and solve for whatever you don't know. Typically you're going to know the molecular weight. You either don't know the grams, or you don't know the time, or you don't know the current. These are definitely given to you in the reaction though. And the one beneath it, well, it should say iron plus 4, but yeah, the iron plus 4 is solved the exact same way. You just change the coefficient on the electrons from 2 to 4. Yeah, I try to set my course up so like the last things we talk about are super easy, so you can focus on all the other projects I know you have to do. Correct. So for your lab notebook, just pictures showing the ones I marked up and showing the ones that you've transcribed since spring break. That's it. Goals to have them all graded by next week. This way Monday I can post all the lab grades. Monday I'm going to have all the homework grades posted, all the quiz grades posted. So that should mean that come Monday, the only grades you've still got missing in the grade book is your final exam. As far as the lab practical, I am going back over them because there are WebAssign's not, or Blackboard's not so great at free responses. So I am going back through your lab practicals. If you don't do well on them, check back in a couple of days to make sure if I've gone through them. Usually I've been catching a few things where it's not quite catching it. But yeah, if you get like a 40, give me a few days to check on it to make sure that this isn't some weird formatting thing. But yeah, particularly with the free response ones, it's not that great at picking up on patterns. And this is definitely something we found in the CHM152 class I'm teaching, that Blackboard just cannot pick up on text answers. Any other questions? I'm going to go through and check So submit what you have, even if it doesn't have a mark on it. Usually what I'll do is I'll forgive one, and I don't advertise at the beginning of the semester, but generally I forgive one assignment, particularly if you took the time to go back through and actually update it and correct it. I'll give you forgiveness. So for the very first lab, you didn't do the pre-lab, odds are I was going to forgive that grade anyway and just give you marks for what you had written after the fact. Again, I don't advertise this because I don't want students relying on it. But yeah, generally what I'll do is I'll forgive a grade or two. One grade. I'll forgive one grade. All right, Elijah, thanks for sticking it out. As for those of you who are going to follow the live stream later, yeah, this was the last live stream of the semester. Your exam's next week. Make sure you take it. Yeah, take care.